Hi, and welcome to the second part of this video on Memix. In this video, I'm going to show you how to write something like this, how to write a tiny bit of shader code to make what you're seeing right on top of here. What you're seeing is a shader that I wrote that is taking the image that is coming in from the webcam and then is doing some chroma cutting, a chroma that is controlled by one of the parameters here in input parameters in Met. So you can see how now it's like very sensitive and how it's just not at all right now. And then I also generate this gradient background that you see in the back procedurally. Okay, and so I'm going to go over the super basics of shader language, and I'm going to explain how to implement that in the Shadertoy flavor that Memix runs. So join me in some nerdy shader creative coding today and spice up your Zoom life. Great. One of the coolest things about Memix as a project is that it was created by Inigo Quiles and by Paul Jeremias, I believe is his full name, both of whom are the creators of Shadertoy. Shadertoy is like a really cool project. It's an online repository of shaders, and as I explained before, shaders are, I don't really know like how to explain this from in a very technical way, but shaders are basically a way to program how an image should be rendered in a two-dimensional screen, or how a texture should be rendered in whatever is going to be displayed. Um, the idea behind shaders is that shaders are basically everywhere. So if you use video games, if you play video games, if you do 3D modeling environment, everything that you see on your screen has been passed through shader languages. And this is very important because basically all the computer graphics that we have available today in the 21st century use shader language and use shaders as a way to display things on the screen. Why is this important? It's important because at some point, I don't know if it was like the late 70s or the 80s, a lot of companies, different companies were trying to figure out how to make computers display things on the screen. And I do very much like this project because I think it's like a representation of how to do things right. So there were like a lot of different companies that were trying to figure out computer graphics, and then they decided to pitch money. Like they were all going to end up competing with each other anyway. So they all decided to put money together and create a consortium, and then have that consortium create a standard specification on how to do hardware accelerated graphics for computers. And that's where OpenGL and the Kronos group was born from. This is an open organization that is funded by industrial partners, but it has become the de facto standard for doing computer graphics in almost any device, any digital device that I can think of these days. So if you are playing video games or doing 3D geometry of any kind, there is a very high chance, I mean, at 95% chance, that your part of your graphics or part of what you're seeing on the screen has gone through some OpenGL accelerated framework. Okay, and what's interesting about this project is that OpenGL also maintains what's called GLSL, Graphics Shader Language, which is a very simple, very low level language that is optimized to display and to render images on the screen. But what's important about this language is that it's very powerful because first of all, it's hardware accelerated. So this code doesn't really run on your CPU, which is the main unit that runs most of the code in your computer, but it runs over your graphics card. And that is an advantage because also, and that's the other property of this language, it's not a serial language. So for example, if you have a screen and you have like 1,000,000 pixels in that screen, it doesn't calculate the color of that pixel one at a time, one after the other. That would be like the serial way of doing it. because it's hardware accelerated and your GPU, your graphics card, is optimized to perform millions of operations in parallel, then with this language, you can calculate the value of each one of the color of those pixels in parallel, all at the same time, which is one go. That's why it's so performative. That's why it's so fast, and that's why when you play video games, you can get like 60 frames per second, even though you have like millions of triangles, tons of light sources, tons of textures, etc. What makes this really interesting is that it's such a low-level language that it's mostly based on very simple mathematical function rules. But what's really cool about this is that with very simple mathematical logic, you can get really, really complex results. So by the end of this video, I'll point you to some resources on how to see examples of that. But before we get into customizing Memix and writing our own shaders, let me first do a really, really basic introduction about the logic behind writing shaders, okay? And I'm going to use some diagrams for that. Let's imagine we are writing a program where we're trying to render an image, where we're trying to decide the color for each one of the pixels of a particular image. And I have sketched a really basic image here. It looks terrible, obviously, but this image is basically, what is it, 7 pixels in this direction by, I haven't counted them, but maybe like whatever, 9 pixels on the other direction. It doesn't really matter. So the way we do this with shader language is that the first thing that we have to keep in mind is that when we write shader language code, what we're doing is we're trying to decide for each one of the pixels individually, we're trying to decide what the color of that pixel is going to be. It's just as simple as that. The only thing that we need to calculate is what is the final color of this pixel going to be. And another thing that we need to keep in mind is that because of the parallel nature of this computation, so like I was saying before, we're not doing a process where we're calculating this pixel, this pixel, this pixel, this pixel, this pixel, one after the other. No, we are calculating all of them at the same time in parallel. Then another thing that we need to keep in mind is that we somehow have very reduced information about the overall state of the image. The only information that we have is information about the particular pixel that we're at. So very often we will know for every single pixel that we are at, we will know, for example, the coordinates of that pixel. So I'm going to say that this coordinate, if we start with 0, 1, 2, 3, 4, 5, and 6, then this pixel is going to be probably in coordinates 5 and, I don't know, 4 in Y, for example. So we will know that for every pixel, and we will have some additional information coming in from the external kernel that is calling our shader program. And we will have reduced information such as, for example, we will have information about how big is the image that we're working on. So we will say, like, the image is 7 by 9. Okay, this is terrible. The image is 7 by 9. We will know that. We will also know things such as, for example, which frame are we at? So how many frames have been rendered already? So you have rendered 241 frames so far, which if we're working at 30 frames per second, which is a very common rate for video, for example, it will mean that we're about 8 seconds 8 seconds into our program. And we will sometimes know additional things, such as, for example, in the case of Memix, and in the case of working with a feed that is coming from a webcam, we will have access to perhaps a texture. And the texture will have a lot of pixels already. We will have access to a texture that is coming from the main program, and that we will be able to look at individual pixels so that we can make decisions out of those pixels. In this case, the texture that we will be using will be the actual image that is coming from the webcam, and then we will be able to look at those pixels and do some manipulations with those pixel colors. Okay, these things that I have explained here, so this information that is coming from the main program into our shader code, and that we will use to calculate the color of this particular pixel, these are called uniforms, usually in shader argot. And then I will explain how to know which uniforms you have available, and I will explain how to use them. Okay, so let's go back to our main. Let's go back and see how we can write a little bit of this for Memix. Okay, cool. The first thing we're going to do is we're going to find in our system where the file that contains the shader code for the custom shader is located. And for that, we're just going to open a new browser window. Okay, and I'm going to, in my system, I'm going to go to my main hard drive C. I'm going to go to users. I'm going to go to my username, Jose Luis. And you can see that I have a bunch of folders here. I know I have here application data, but I have it enabled because I have on my Explorer window, I have enabled hidden files. So I can click here, app data, local, and then BeautyPie, which is the name of the company founded by the Shadertoy authors, and then Memix here. And you can see that we can find in shader here, this is the main file that I can open with code. And so if I open a Visual Studio instance here and I drag my shader file, you can see that this is the file that has the code for the main custom shader that lives in Memix. Okay. If you have trouble finding this, root, something that you can do is you can do the following. You can copy paste here. You can copy paste this way of localizing what is your home drive and what is your home path. All right, and then you can write here. App data, and then you can write here local, and then you will land in what are the files in your local system, and then here you will be able to find BeautyPie and then Memix. Okay, so I have a shortcut in my system to this folder because I never remember what it is. So you feel free to make yourself also a shortcut to this. Okay. All right, so we're good. Now I have here shader.txt. This is the main file that has the shader. And this is a little hard to read. So what I'm going to do is I'm going to invite you to go to the extensions manager in Visual Studio Code and type GLSL, and you will find that there are many applications, many extensions that allow you to apply syntax highlighting to this code. So for example, here I'm going to click here plain text, and I'm going to scroll down to Shader Lab, which is an extension that I already installed in the past, and that it gives me very nice highlighting so that I can see what comments are, what functions are, and what other things are. Okay, and now that we're here, let's try tinkering a little bit with this, and I'm going to explain you like the super basics of shader language. Okay, now that we're here, let's go a little bit over the basics. Okay, so what you can see is on the right hand side here I have the main shader file that runs the custom filter that I have here. So this filter is right now doing this twisty thing, but just because this is the code that I have on the right side. Whenever I change that, this custom filter will also be updated. And you can see here that what I have on my left hand side is all the way at the top, I have a Zoom meeting that is running from the Memix virtual webcam. And here I have the Memix UI that is letting me switch between different filters. And I want to see this because I want to see how the changes that I make on the right hand side affect the streaming of the webcam that I'm doing on the left hand side. Okay, so going back to the idea that I was discussing before, what I was saying before is that when we have a pixel, the pixel that we're working, remember, shader language is just writing code that is going to be run on every pixel of the image. So, and as I was saying before, every pixel has very reduced information. the pixel knows only what the main program is giving it as information. And I was saying that those are called uniforms. So if you go here to the main code, you can see that we have some helper comments here that tell us that this shader is getting some uniforms coming in from the main program. One of them is the time that has elapsed in seconds while running this shader, the number of frames that have elapsed over the course of running this program, the resolution of the screen, so how many pixels by how many pixels the image that we're computing has. These are values for the two sliders that can customize the slider, the shader, and then channel 0 has a texture that is the actual feed of the original webcam that is being brought into the filter. Okay, I will explain more about those in a second. What I would like to highlight as well is the kind of types that these things are. So you can see, for example, that time is a float, and it makes sense because if it's in seconds, then we want to have decimal precision. The number of frames is an integer because we cannot have 2.3 frames. And then the resolution, for example, and this is interesting, is a vector with 3 components. You have heard me say a lot how points and vectors are the exact same thing basically, and vectors are just lists of numbers, one after the other. So what we can see here is that the resolution is a vector, but the x and y properties are the width and the height, and then z gives us information about the cropping of the image. Then this is an array with 2 values, each one of them being a float. Those are the values of the sliders. And then the texture that is coming from the webcam is this thing called sampler 2D, which for the time being, let's think about this as a texture. Let's think about this as an image that has pixels in the 2 directions, okay? Then what you can see here is that I have a bunch of code, and this code is the code that is running the custom roto twist filter that Inigo Quiles created. And if I comment everything out, so I've done, because I don't know if this is coming from Shader Lab, but I've done Control// and everything gets canceled out. If I save this file, you can see that nothing happens. And what I'm going to do is I'm going to copy this here so that I create an empty main image file. Okay, and I have saved this. What this has done is that it has updated the custom filter, and you can see that the custom filter is basically now a black image because I am doing absolutely no calculations in this shader. So all the pixels are by default, they're just black. Okay, now why did I do this? I did this because shaders always have a main function. In this case, it's called main image, and that function usually takes the coordinates of the point that we're in, as that's an uniform, and this is, you can see, it's a vector with 2 values. So here I will be able to know the x location and the y location of the pixel that I am at right now, and what I'm required to return from this function is a vector with 4 values, which is going to be the fragment color. So basically the color of this filter. Fragment is a technical word that is used in shader language to define I don't know how to explain. I don't really know how to explain this properly, but basically like to define the unit of computation that we are working on. In this case, it's going to be a pixel. Okay. Now, why is it vec 4? Why does this vector has 4 components? Because it has the RGB components, the 3 colors, but it also requires the alpha output, which is the 4th one. Okay. All right, and I would like to remind you that in this case, in Memix, we're not working with pure GLSL language. We're working with the Shadertoy flavor of GLSL. That's why we have these particular uniforms. Those are provided by the Shadertoy framework, and that's why we have some of the functions are specific to the Shadertoy environment. The language is like very, very similar. It's like 90% similar, I would say. It's just the uniforms and a few minor functions that change between the original GLSL and this implementation. This is a very common thing to do, to write an implementation of GLSL customized to your programming language or to your environment. Okay, so let's now that we know how to create a black filter, how about we start tinkering a little bit with different colors? Okay, let's see some examples of how can we customize our shader. The first thing I would like to do is I would like to write a shader that just outputs very basic colors like black, white, red, etc. And we have already done this with here by writing an empty function, but I would like to do this a bit more programmatically. So the first thing that I would like to do is I would like to define a color that has parameters that I want to define. So for example, colors, because they have three values, they are represented as vec3 types, so a vector with three values, and I'm going to call this pixel color, for example, the color of the pixel that we are at. Okay, and since I'm going to write something where it makes all the pixels, for example, it makes them black, so what I'm going to do is I'm going to create a vector with three values, and each one of them is going to be a float 1.0. Okay, and then I'm going to return, I'm going to say that the frag color, the color of this fragment of this pixel is going to be equal to this color that I have defined. I'm going to save this and nothing happens. So I'm going to change this to white so that we can see the effect of the color that we have defined. I'm going to save this now, and it's also not updating, and I'm not sure why. Oh yeah, sorry, because I forgot that frag color is a vector with four values. So vec4 is going to be equal to, I'm going to write this dot y pixel color dot z and 1.0, for example, as for the alpha value. I'm going to save this, and it still doesn't work. Oh yeah, that was very dumb. It was actually updating. It was just that I was saying that I wanted a black color, so that's why everything was turning black. But if you see here, if I now change, for example, the first channel, the red channel, to 1, every pixel gets a red color. If I change the second one to the green channel to 1, then everything is going to turn yellow. And then if I change the third one to 1, all the pixels are going to turn black, are going to turn white. I can also do cyan, or I can also do pure blue, you know? Just because I'm defining a variable called the pixel color. I'm specifying the three values for each one of the channels, and then I'm using that to define a vec4, a vector of 4 dimensions for the frag color, which is what I ultimately need to define before I leave this function. And I'm using the XYZ of this color, and I'm using 1 as the value of alpha. Okay. Now you may wonder, why are you using here ones and zeros if I've been using 0 to 255 all my life in my web development course, or in my Photoshop life, whatever. It is true. Colors are typically represented with values between 0 and 255 in other environments, but in shader language they are normalized. So their value is going from 0 to 1. That's it. It's just a convention that happens here. Okay? What are other things that we can do? So this was very simple. We just defined one color, the same color for all the pixels, but for each pixel we can customize that color if you use some of the external information, some of the uniforms that are coming in. So for example, every pixel is getting a vector called fragment coordinates, which tells the pixel where in the matrix of pixels in the image it is. So for example, here I can say in fragment coordinates, I can say, for example, integer x position is going to be equal to frag coordinates dot x, and then another integer y position is going to be equal to frag coordinates dot y. Sorry for frag coordinates dot y. Okay, so now with those two values, I can now make decisions about how to render this pixel. So for example, let's say that I want to write a shader that just draws like horizontal lines, black and white, every single pixel. Something that I can do is I can find if, for example, on the y direction, if this pixel is even or odd, and if it's even, I can make it black, and if it's odd, I can make it black, for example. So something that I can do is I can say if x position modulus 2 equals 0, so if this pixel is even, sorry, in y position, if this is even, then so for example, I can initialize pixel color, and I can say pixel color is by default is going to be black, and I can initialize vectors with 3 values with the same value, just writing 1 here. It's a shortcut, okay? But I can say, well, but if it turns out that this pixel is in an even position, then let's make that instead, let's make it white. So I'm going to say vec3 and full white. And then here, I can still keep this here, and this is not working again. Yes, I found the problem. I was doing something not great, so I was taking the x coordinate of the fragment color, which is a float, and I was trying to convert it automatically to an integer, and that doesn't work. So I need to cast with a function. I need to cast this value to an integer. I need to forcefully make it an integer before I do any computation with that. And if I save that, you can see that now I can use the modulo operator here. And what is happening is that in this image, I'm getting horizontal lines. The ones that are black are the ones that are on an odd position, so 1, 2, 3, 5, etc. And the ones that are white are the ones that have a y position that is even, so 0, 2, 4, etc., etc. I could very simply change this and now turn it into vertical lines just by looking at the x position, for example. And something that I haven't explained before is that I can, you see how I'm taking, to create the fragment color, I'm creating a vector 4 with 4 coordinates, but I'm taking x, y, and z. Because pixel color is a vector with 3 coordinates, I can shortcut this just here and then say I'm going to create a vector of 4 components with the 3 components that are here and a 4th value here. And this still works. Okay? Wonderful. So how about another thing? We can also create a gradient that goes from black to white as a shader. We can do this. We can do that. For example, I'm going to clear everything because we know where we are in the vertical direction. We know that fragment coordinates is giving us the pixel value of where we are in the vertical position. We can write a very simple rule where we decide, well, if we are all the way at the top, we want the color to be black, so we want 0. And if we are all the way at the bottom, we want the color to be white, so we want 1. So we can write a very simple rule where we say, can I find how far along in the height mi is this pixel? And that relation is going to be very simple. It's going to be the value of the pixel location, so 1, 2, 3, 4, 5, 6, whatever, divided by the total amount of pixels in the vertical direction, the height of the image. So if the image is 800 pixels tall and I am at pixel 400, then my pixel normalized pixel coordinate is going to be 0.5. Okay, so that's very easy to calculate here. So for example, I'm going to say float v, which is going to be the normalized coordinate of this pixel in the vertical direction, is going to be where I am in the overall pixel. so fragment coordinate y, so the y coordinate of this pixel, divided by the height of this image. And you can see that from the uniforms, I have I resolution, which is a vector of 3 coordinates, right? So if I take the y coordinate, that's going to give me the height. So v is going to be the normalized location in height, and then I can go back to creating my pixel color variable and then just give it the value of v as an input. And as I do that, ta-da! I get a gradient that is going from black to white horizontally. Okay, if I were to change this to just look at the x, and this would be, I would want to change, for example, this to u, for example, then I can have a horizontal. And if you don't like the direction, you can just invert that by saying 1 minus the value, okay, and that will flip the direction of the gradient. Okay, so I'm gonna keep it vertical. So 1 minus the resolution in y and v. Okay, and I'm gonna have it the other way around here, like this. Okay, and I'm gonna keep this for something that I want to do later. Next thing I'm going to do is going to be super simple. I'm actually going to take the webcam feed. I'm going to take the image that is coming from the webcam, and I'm just going to display it as it is with no single changes. Okay. If you remember, we had iChannel as an uniform that we could use to read information from that image. So what I'm going to do first is I'm going to compute the relative location of this pixel, so the normalized location in this frame. Okay, so we know that frag coordinates give us pixel coordinates, so 0, 1, 2, 3, 4. I'm going to turn that into something that goes from 0 to 1. Shader language is very elegant in that it allows you to work with vectors. So something that I can do is I can say I can divide frag coordinate, which is a 2-dimensional vector. I can divide it by I resolution dot x and y. So I can divide the two. I can divide the vector with 2 coordinates by the 2 coordinates of the I resolution vector, and this will give me a vector 2 object. I can now, for example, just going back, if I wanted to go back to the gradient, I can just take from this 2-dimensional vector, I can take the x component, or I can take the y component, and then I can change the direction of the gradient. Okay, and I'm going to use that because textures, when they come in, they don't come in with pixel coordinates. They come in normalized coordinates. So in order to take the color of a pixel in a texture, I need to address that pixel by its normalized coordinates. So what I'm going to do here is I'm going to use the texture function to read from I channel 0, and I'm going to read the UV coordinates of the pixel in the normalized coordinates U and V that I have already requested for this particular pixel. And you can see that this is currently not working. Yes, sorry. I think I crashed my Memix, so I restarted everything. I restarted the call and restarted the app. And then what I did was texture returns a vector of 4 coordinates. So I was having problems fitting it into a variable with 3 coordinates. So what I did was I just requested from the vector with 4 coordinates, I requested the 3 first coordinates, x, y, and z. And that's what I'm using for the pixel color here. And now I'm creating a 4-dimensional vector with those 3 channels plus the alpha. Okay. What you can see is that we have something weird, which is that my image is flipped. And my image is flipped because I believe the coordinates of the image of my webcam are somehow flipped for some reason. So what I'm going to do is I'm going to flip those manually, just like I did before. So I'm going to comment this out, and I'm going to say vector 2, u is going to be the fragment coordinates of x divided by the I resolution x. and then vector 2v is going to be fragment coordinate y divided by I resolution dot y, and vector 2 uv is going to be equal to a vector with these two components. Basically, this that I have written here is the same thing that I have written here, just more explicit, okay? But I did that because now if I want to flip the vertical component, then I can just do 1 minus this component, and then everything gets flipped. Yeah, another rookie mistake. This is not a vector 2. This is just a float. This is just a one single number. So as I do this, now this works exactly. So this is one value, another value. I create a two-dimensional vector with the two values, and then I use that to ping the image and to get the coordinates of to get the color of each pixel on the webcam that is coming in, and just using that right away as an output. Okay. Why is this interesting? It's interesting because now I have here in a variable, I have the color of the pixel that I am in, but from the webcam feed that is coming in. And because I have the color, I have the three numbers, I can do manipulations with those numbers. So for example, let's say I'm going to use, for example, only the red channel. So here, instead of pixel color, the XYZ, I'm going to just replace this with just using the red channel, XXX. So for example, as I do this, what you can see here is that I turn my image black and white, but it's not really black and white. It is more of a just looking at the values of the red channel. If I do YYY, you would see that I see only the values of the green channel, and you can see that my background is now very bright. You can see Z is only the blue channel, so it makes everything a bit more homogeneous. And I can also take the value. So if I do X, Y, and Z, that's the original color. But I can take the RGB, which again are the X, Y, Z, and I can swap them and I can combine them. So for example, I can say, instead of RGB, I'm going to use the value of the blue channel, Z, in the red. I'm going to maintain Y, what it is, the green, and I'm going to take the value of the red channel and use it in the blue channel. So that's going to be X here. And as I do that, you can see that my color distorts. And then I can do other combinations, X, red, green, red. Or I can do blue, blue, red, green. Or, and I like this one for some reason. Or I can do red, red, green. Or I can do green, green, blue. Or I don't know, I can do other combinations, you know? Something that I can do as well is I can convert the image to black and white by, for example, looking at the XYZ values and calculating the average. So for example, if I say float the value of the brightness, I'm just going to do B. The value of brightness is going to be equal to pixel color, the green, so the red value, multiplied by 0.333, okay, plus 0.333, so a third of the value for the green channel, Y, plus 0.333 times the value of the red, of the blue channel, so Z. And then I can use that to say BBB is going to be equal to the three channels of the image are going to be the brightness that I just calculated. This black and white conversion would be a bit more accurate because it's taking the average of the three channels as opposed to just one channel or the other. And actually, for those of you who are a bit more nerdy about image processing and color, actually using thirds is not exactly how it's done in industry, because I believe there is an understanding that human perception of the eye has like different perception for different channels, so it needs more green than red, etc. So it's a very common thing to not average, when you do black and color conversion, not average them completely equally, but depending on the standard that you're using, use different proportions. So for example, here for Luma Video, they use a different ratio. They use here, they use 299, and here they use 587, and here they use 114. And as I save this, let's see how different this is. As I save this, you see, I get a little bit more contrast, which I think it's interesting. So that can be, it's up to you to choose what you want to do. Okay. Now, another thing that is really interesting is that, remember how I was, if I cancel this out and I go back to pixel color here, remember how I'm using a chroma screen? So one of the interesting things is that because I have found the color of each pixel in the webcam, now I can take a look at that color and make decisions based on the values of the RGB channel. So the way you do chroma, for example, is you say, let me look at the pixels in every image, and if the color of that pixel is around, is nearby the color of the chroma, then I'm just going to remove that color and switch it with something else. So for example, that's going to be, at a basic level, it's going to be quite easy to do. I can say, I looked it up before, and I know that my that this chroma that I'm using right now has more or less, this chroma has more or less these values. So it has 99. So this green that you're seeing here is 99 red, is 205 green, and 164 blue. So what I can do is I can normalize that. So I can, with a calculator, I can say, well, 99 divided by 255 is 0.38. So that would be 99 in normalized coordinates. So what I can say here is, if pixel color X, the green, is greater than, we said it was 30.38, if the color is greater than 0.30, and it's also less than 38, I'm going to say 0.45. So I want a range, because not all the colors are the same. And for example, if the green channel, we said 205, so 205 divided by 255 is 0.80. So if this is greater than 0.70, and pixel color is Y is less than 0.80, so 0.90, and pixel color Z is greater than, where were we? So 164 divided by 255 is 0.65 more or less. So if this is greater than 0.55 and is less than 0.65, 0.75. Okay? If all of this is true, it means that the color that I'm in right now is very close to the chroma color. And if that's the case, what I want to say is, instead of piping this color out, I want to replace it with another color. What color can that be? For example, I'm just going to replace it with black, for example. I'm going to say, if that was true, then pixel color needs to be replaced with a new vector 3 black. And as I do that, okay, you guys see it's not perfect, it's not great, but you can see that more or less the range of pixels in the chroma are being replaced. So I can replace this with, for example, red. This is going to look terrible. I can replace this with red, or I can replace it with the V coordinate of that I calculated before. So the normalized value along the Y, substituting it with a gradient, you know? I'm sorry it took a little bit, but yeah, it's or the thing is, like, this is not perfect, So if you go down to the code that Inigo provided for us, here there is this one function that actually gives us a much better implementation for chroma key detection. So I'm going to copy this and paste this here. Okay, I'm going to uncomment it, and I'm going to I'm not going to explain the math here because I don't really know that well how it's working right now. But what I'm going to do here is I'm going to say I'm going to compute here the value. I'm going to remove all of this. Okay, I'm going to compute the value of the chroma, and I'm going to pass here the pixel color that I just created. As I do this, oh yeah, another rookie mistake. This function, I declared it after, but if I do that, then this function is not in memory. This function is not in memory when this gets called because shader language doesn't do function hoisting. So I need to define that beforehand. And if I do that, now this function exists. Well, this function exists when this is called, so I can do like a proper chroma change here. And something that I can do now is I can say, well, k is giving me a value from 0 to 1 that tells me basically how much of a chroma I am at. So 0 means no chroma and 1 means full chroma, because it also, you see like the edges of my shape, they also have like, they do some blending. So what I can say here is I can say if the value of k is greater than 0.1, for example, then apply this this gradient that I was talking about. Okay, so you can see that I have some pixels here in my body because this probably have some degree of green, but maybe this is something that I can use for as a parameter. So maybe I can use these sliders here to tune that in. So for example, if e is greater than I param 0, and then if I change this, you can see that that value, yep, I get more or less sensitivity in the chroma. Okay. All right, that was a lot, right? Okay, I think with this I'm gonna wrap it here, but I would like to point you to other references of where can you learn more about shader language, and where can you where can you learn more about this. Shaders and shader language are everywhere, and they're everywhere that in every framework that does any kind of image output on a computer screen. And unfortunately, for the reasons that I explained at the beginning of the video, it's a very standard language. It's very homogeneous. So if you learn the basics of shader language, you will be able to port that knowledge to like a lot of very different frameworks. So a really good place to start is the Book of Shaders by Patricio González Vivo and Jen Lowe. It is a very, very low level introduction, and it goes like very, very step by step. So I very strongly suggest that you check this out. If you're in the processing world, in the creative coding sphere, Andres Colubri wrote a very good introduction to shader language as well. This one is a bit more oriented towards three-dimensional geometry. And because remember that what we saw today is very much for 2D images, but shader languages actually are very powerful when it comes to rendering meshes and rendering triangles in three-dimensional space. We have not looked at that technique yet, but I will hopefully at some point in the future record some tutorials about 3D geometry, triangles in space, and shaders, and how to reconcile all of that together. And definitely, if you want to learn more, you should check out Inigo Quiles's YouTube. He is one of the creators of Shadertoy. He's one of the creators of Memix, and he has a lot of really interesting videos on advanced techniques on about how to think of shaders and how to think about mathematical equations and how to use them to generate form. It's really, really cool. And he actually recorded this tutorial here specifically as a guest lecture for the class that I teach at the GSD, and he in which he explains how to construct a Greek temple from scratch. And what's so cool is that you see this image here. There is not a single triangle on this image. Everything is generated with mathematical functions and with simple numerical rules. It's extremely, extremely fascinating. I love shaders. I think it's one of the coolest things ever. So I really strongly, if you're nerdy enough and you have the patience, I really strongly recommend that you follow some tutorials and that you try it out. Go to Shadertoy and look at what's out there. It's really, really cool. And you're going to learn a lot about creative coding if you get into shaders. I may do a third iteration of this series where I go to Shadertoy, I take one of those shaders and I port it to Memix. That could be an interesting exercise to do. So perhaps if I do that, you will see like links somewhere here and here. Okay, thank you very much.